of slip, let us take it as torque speed. Both are same. Okay. Slip varies opposite to that of speed. If speed is varying from left to right, slip will vary from right to left. That is the only difference what we get. Okay. Now, let the speed here be 0. The speed here be ns. Okay. So when speed is ns, I should be marking the maximum torque line. So this is T max. Okay. So when the speed is between 0 to ns, the machine is acting as a motor. So when the machine is started, okay, when the machine is started, the torque developed is starting torque. Okay, but when the slip of the machine is 0, okay, let us consider TR is equals to K1 S E2 square R2 divided by R2 square plus S into X2 square. So when S is equals to 0, that is N is equals to Ns. So when N is equals to Ns, my slip becomes 0. At that time, torque is 0. So as the slip increases, okay, as the slip increases, then the torque also increases linearly, or I will take a different color. Okay. As slip increases, the torque increases linearly. Oh my God. Okay, and it reaches the maximum value, and after that it will fall down. It will come to a certain value. Okay, now when the plugging occurs, this is the characteristic of a motor when the machine is operating as a motor. Now when the plugging occurs, the supply is reversed. Okay, when the plugging occurs, the supply is reversed. Then the moment supply is reversed, the RMF developed in the stator will reverse. Because RMF reversed, the speed of the motor will also reverse. Okay, so when the plugging is done, the motor starts running in opposite direction. For a moment, I will consider that as a negative speed, the speed below 0. Okay, so when plugging, or I can write here, when operating as motor, slip is equals to ns minus n divided by ns. Okay, so therefore slip is, when operating as motor, slip is, okay, 0 to 1. When plugging is done, my slip is ns minus of minus n divided by ns. So my slip is greater than 1 because it is ns plus n divided by ns. It will be now ns plus n divided by ns. When the motor starts rotating in opposite direction, I can consider slip greater than 1. It will be more than 1. Okay. So now, but this will not exist for a long time. This is momentary. Okay. This is momentary. Okay. This is momentary. Momentarily it will happen. So therefore, when the plugging is done, when the machine is operated as a brake, the speed is reversed. Okay, and therefore the characteristics, suppose it can be up to ns minus ns, and the characteristics goes like this. Okay, so this is brake. Machine is operating as brake. Now this is torque. The torque is still positive. The torque is still positive. Positive torque in the sense the torque that is developed by the rotor and delivered to the external load. That is positive torque. Okay, that is positive torque. Now, when the machine is operated as generator, when the machine is operated as generator, the torque is not developed by the rotor. The torque is externally supplied to the rotor. Therefore, the direction of power flow to the rotor is opposite, or the direction of torque to the rotor is opposite. Okay. So when motor, okay, when induction machine operates as motor and brake, torque is developed in rotor and supplied to load. Okay. So this we consider it as positive torque. This we consider it as positive torque. Now when operating as generator, when the machine is operating as generator, we know we are giving external mechanical energy to the rotor. Therefore, the torque is now supplied from the external source to the rotor. And the direction of torque is not from the rotor to the load, but from the prime mover to the rotor. Hence, the direction of torque is negative. In such case, the torque slip characteristics or the torque speed characteristic will be like this. Up to 2 ns. This is minus Tmax. Minus Tmax in the sense magnitude of the maximum torque is same, but only it is given externally. Okay, so this is generator. Okay, so when induction motor operates as generator, torque to the rotor is externally supplied okay, and is taken as negative torque. And is taken as negative torque. So this is the complete characteristic of induction machine operating as motor, brake and generator. Okay. Any doubts in this?
No, sir.
Okay. So then we will move to the next topic and next module only, power stages in induction motor. Actually, the first topic is your what is it? Phasor diagram. Okay, phasor diagram of, we will start from there only then. Phasor diagram of induction motor and its equivalent circuit. Then we will move to the power stages, or because what we'll do, okay, we'll finish first power stage, then we'll move to phasor diagram. Power stages in induction motor. Because we are fresh with the torque developed and all, we will finish that. power stages in induction motor. Okay. Now, we know that in an induction motor, let me draw it here. Let this be stator. Let this be rotor. Okay. So this is stator and let this be rotor. Okay. So when I give a three-phase supply to this stator, a three-phase magnetic field is produced. That three-phase magnetic field will rotate in the air gap. When that three-phase magnetic field rotates in the air gap, that is cut by the rotor conductors due to relative speed or relative motion, and an EMF is induced in the rotor conductors. Since rotor are short circuited, the current is flowing in the rotor conductors and a torque is developed, and hence the motor starts running. So from the point of application of supply to the point of rotation and the torque available at the load, there are various stages. Okay. Now the moment when the supply is given, that supply first has to satisfy the stator requirements. Okay. First has to satisfy the stator requirements. What stator has got? Stator has got, what are two major things in stator? Winding and what is the next part? Stator core. Okay. So the slots are punched in stator core itself. Okay. We have stator winding and stator core. Now winding is having its resistance. Okay. Therefore I get copper loss. Stator core is made up of any practical material. Therefore it has got iron loss. So before the power is available after the stator, the input supply must satisfy stator copper loss and stator iron loss. Then the remaining power from the source input is supplied to the rotor in the form of rotor input. Okay. Then when rotor input or rotor receives the input, what rotor has got? Rotor has got rotor winding or rotor bars. Rotor has got rotor winding or rotor bars, and also it has got rotor core. Okay. So these rotor bars or rotor winding are having resistance. Therefore, we get copper losses. But here, iron loss are neglected. Rotor iron loss are neglected during running condition. Because why? Can anybody tell? Guess why? Quick. Am I audible? Still we are in connection?
Yes, sir.
Yeah. Why we have to neglect rotor iron losses? Because rotor frequency is very low. Okay, f dash is equals to s into f, and s is less than 10% for normal conditions. So since the frequency of rotor induced EMF and current is very low, the iron losses in the rotors are very low, hence this can be neglected. But that doesn't mean that I should not use the laminated core. Still the rotor is made up of laminated core. Okay. So what are the different losses present here? Till now, when the stator receives the supply, stator supply will satisfy the stator copper loss, okay, and stator iron loss. After satisfying stator copper loss and stator iron loss, it will send the remaining power to the rotor. Now, when the remaining power is available at the rotor will consume some amount of power in the form of rotor copper loss, rotor iron losses are neglected. Now, there is power available to the rotor to develop the mechanical power. So, all the power that is received from the stator after satisfying rotor copper loss, the power is developed in the rotor, and this is known as gross power developed. This is known as gross power developed in the rotor. It is exactly like the gross torque or gross power developed in the armature of the DC motor, PA. Now, is PA is equals to PSH or P out? In DC machines, we have solved so many examples. Was PA is equals to P out? Was armature developed power equal to the shaft power or the output power? I'm asking. Was it equal?
Yes.
Then I should close my shop and get lost from the college. If you say PA is equals to P out, if armature developed power is equal to output power, then I should stop teaching you the machines. Then who is satisfying
Not
rotation motors? Okay. So the remaining amount of power after rotor copper losses is the power developed in the rotor, which is called gross power developed. That gross power will also satisfy the rotational losses, friction and windage loss in the motor. Remaining power after satisfying friction and windage loss is supplied to the load in the form of output power. Okay. So from the input to the output, there are various stages of power with respect to losses. First, stator copper loss and stator iron loss. Then remaining power is given to rotor. Then there will be rotor copper loss. After rotor copper loss, gross power is developed in the mechanical power is developed in the rotor. And after that, the frictional and windage loss are satisfied. Then the power output is supplied to the load. Okay. So if I put this in the form of power stage, I can write here motor input to stator. I take this as P1. Then this power P1 first satisfies okay, stator copper loss, stator copper and iron loss. Then remaining power is given as rotor input P2. Then there exists rotor copper loss. Then remaining power after rotor copper loss is developed in the form of mechanical power. PM or gross torque. Mechanical power is torque, TG, gross torque. Then out of this power developed in the rotor, some is utilized to satisfy friction and windage loss. Okay. Then we'll get rotor output, or that is P out, or shaft torque. Shaft torque. So these are the different power stages in an induction motor. Okay. So first input is given, stator copper loss and iron losses are satisfied, remaining is given as input to the rotor. Now out of that in rotor input, rotor copper losses are taken out, then mechanical power is gross mechanical power is developed in the rotor. Then if that gross power will satisfy the friction and windage loss or rotational losses in the motor, and remaining power is available at the output. Okay, so now we have to put all these things in the equations. Now we can say a torque developed by induction motor. So whatever the torque equations we have seen the electrically developed torque, which was having the parameters like voltages, currents, resistors, reactance, flux, and slip. Now purely we will look into the equations which are mechanical by nature in terms of speed and power and torque. Okay. So here we have seen the induction motor will develop a gross torque in the rotor. Okay. So until this point, the speed is ns, because until this point the motor is at standstill. The motor starts rotating only when the friction and windage losses are overcome. Now here the motor is rotating. Okay. So if I want to use the equation for Tg in terms of speed, the speed considered should be the synchronous speed. So here I can write, okay, torque developed by induction motor. I can write torque Tg is equals to P2 divided by omega s, or I can write this as P2 divided by 2 pi ns by 60. Yeah. Or if we go with the classical equation, we'll take out all these things. Input power to rotor is I think that is not TG. Input power to the rotor given by is given by P2 is equals to 2 pi ns Tg by 60. It is 2 pi nt by 60. We have the power equation in terms of torque. Okay, or this is what? 9.55, not 9.5. How much is this? Oh no, that is torque equation, not 9.5. Okay, this is input power. Because input power is transferred from stator to rotor. Input power is transferred from stator to rotor at ns because there is a rotating magnetic field. Now, when the mechanical power is developed, in the rotor, then the rotor starts rotating at speed n. The rotor starts rotating. Actually, this arrow mark should come here, and this arrow mark should come here. The rotor starts rotating at speed n. Therefore, or here I can write or Tg is equals to P2 into 60 divided by 2 pi ns, where ns is in RPM. Okay. Some books they have followed 2 pi ns into Tg, taking ns in RPS. Okay. Take this as equation 1. Then power developed in rotor is input power to the rotor is given at speed ns. Power developed in rotor is at speed n. This is a difference. Okay, this you should note. Therefore, Pm is equals to, I can write 2 pi n Tg by 60, or Tg is equals to or Tg is equals to Tm into 60 divided by 2 pi n. Okay. Now equation 1 and 2 are one and the same. Here equation 1 and 2 are same, as both give the gross torque. As both give gross torque developed in rotor. Okay, so either I can express my gross torque in terms of power developed in rotor, or I can express my gross torque in terms of power input to rotor. If I consider power input to rotor, then I should consider synchronous speed. If I consider power output of the rotor or gross power of the rotor, I should consider actual speed, that is rotor speed. So this care must be taken. Then the output power is given by The power output is given by P out is equals to 2 pi n TSH by 60, or shaft torque TSH is equals to P out into 60 divided by 2 pi n. This is equation 3. So this is gross torque, where Tg is gross torque. This is output torque or actual torque or useful torque or the shaft torque. Okay, so I can write here, we can write Tg is equals to, okay, 60 by 2 pi, it will be 9.55. 9.55 P2 by Ns, or Tg is equals to 9.55 Pm by N, and TSH is equals to 9.55 P out by N. So these are the torque equations in terms of mechanical quantities. Okay. Is it clear?
Yes.
So next we shall see torque, then mechanical power, and rotor output. Okay. So in the power flow equation, or sorry, power flow diagram, P1 is the input power. Okay, P1 is the input power, which is equal to rotor input plus stator copper loss and iron loss. Is it true? Yes or no?
Yes, sir.
Okay, so this rotor input, this is also a stator output, or I can write this as stator output. Can I write it as stator output?
Yes, sir.
Okay, so when I have deducted the stator losses from the stator input, remaining is stator output. So the motor input P1 can be motor input you can call, or stator input you can call, both are same. Okay, so the stator input P1 is equals to the stator output plus stator losses, right? The same thing I will write here. Stator input P1 is equals to stator output plus stator losses. Stator output plus stator losses. Okay, so stator output is nothing but my rotor input. Yes, so here stator output, okay, is nothing but rotor input. Okay. So I can write P1 is equals to P2 plus stator losses. P1 is equals to P2 plus stator losses. Okay. Then the rotor input if you see in the diagram, the rotor input is satisfying rotor copper losses and remaining power is developed in the form of rotor power output. Is it? The rotor input is equals to rotor copper loss plus the power developed in the rotor. Okay. So rotor input P2 is equals to power developed in rotor plus rotor losses. So in the rotor, there are only rotor copper losses. Iron losses are neglected plus rotor copper loss. Okay. So I can write or rotor power developed PM is equals to, it is rotor input minus rotor copper loss. That is PM is equals to, I can write P2 minus rotor copper loss. P2 minus rotor copper loss. Also I can write this PM, also we have these equations for TG. Also PM is equals to 2 pi n TG by 60. Okay. Also PM is equals to 2 pi n into TG by 60. Therefore, I can write 2 pi n Tg by 60 is equals to P2 minus rotor copper loss. P2 minus rotor copper loss. Or gross torque developed Tg is equals to, I can write P2 minus rotor copper loss divided by 2 pi n by 60. Divided by 2 pi n by 60. Now, if there were no rotor copper loss, okay, then Tg is equals to P2 divided by 2 pi n by 60. And Tg is equals to 2 pi n by 60. So you take this as what where we have to do? You take this as equation 1, take this as equation 2, this as equation 3. Okay. Now, or I can write Tg is not this equation. I can write Tg is equals to PM divided by 2 pi n by 60. You take this as equation 3 and this as equation 4. If rotor copper losses are absent, then it will be 2 pi ns by 60, not n. You should remember. Sorry, not here. Here is n. This is 2 pi ns by 60. Tg is equals to 2 pi ns by 60. So from equation 3 and 4, from equation 3 and 4, okay, Pm is equals to uh, omega into Tg, and P2 is equals to omega s into Tg. Omega s is synchronous speed, angular velocity, synchronous angular velocity, or synchronous angular speed. Okay, this is nothing but 2 pi n into Tg by 60 is equals to 2 pi ns by 60 into Tg to Tg. So taking P2 minus Pm, that is rotor input minus rotor power developed, then I will get rotor copper loss. That's it. So P2 minus Pm is equals to, I can write here 2 pi ns Tg by 60 minus 2 pi n Tg by 60, or P2 minus Pm, P2 minus Pm is equals to 2 pi by 60 into Tg, okay, into ns minus n. Okay, 2 pi by 60 into Tg, ns minus n. Okay. From equation 2, what is equation 2? It is Pm is equals to rotor input, sorry, P2 minus rotor copper loss. So from equation 2, I can write rotor copper loss equals to P2 minus Pm. Okay. From equation 2, rotor copper loss is equals to P2 minus Pm. You can observe here. From equation 2, rotor copper loss is equals to P2 minus Pm. Okay. And what we have P2 minus Pm, you take this as equation 5. Okay. Therefore, from equation 5, okay, what we can write is rotor copper loss is equals to, I can write Tg into 2 pi by 60 into ns minus n. Is it? Sorry. Tg 2 pi by 60 into ns minus n. Okay. You take this as equation 6. Dividing equation 6 by rotor input, dividing equation 6 by rotor input, P2 equals to 2 pi ns Tg by 60. Okay. Then what I get? Rotor copper loss divided by rotor input is equals to, I have Tg into 2 pi by 60 into ns minus n divided by 2 pi ns Tg by 60. So 2 pi by 60, 2 pi by 60, Tg and Tg will go. What will remain is ns minus n divided by ns, which is equals to slip. Yes. Okay. Therefore, rotor copper loss divided by rotor input is equals to slip S, or rotor copper loss is equals to slip times rotor input. This is one of the important relation that we need in the circle diagram calculations. Okay. Rotor input. So rotor input is nothing but the power across air gap, that is S into P2. Okay. And this is important relationship. And rotor input P2 is equals to rotor copper loss by slip. Okay, rotor copper loss by slip. Take this as next equation. Take this as equation 7, and these both combining as equation 8, because they are the same. Equation 8. The rotor gross output, gross rotor output, PM is equals to, gross rotor output PM is equals to, okay, rotor input minus rotor copper loss. Rotor input minus rotor copper loss, which is equals to, rotor input is P2 minus rotor copper loss is what? S into P2. Therefore, PM is equals to P2 into 1 minus S. P2 into 1 minus S. So the rotor efficiency, if I consider, which is your next class? Babu sir.
Yes, sir.
Sir, just 2 minutes. Shall I continue? Only 2 equations are remaining.
Okay, sir. Okay, sir.
Just 2 minutes. I will end.
Okay, sir.
Yes, sir. So rotor gross output is PM equals to P2 into 1 minus S. You take this as equation 9. Okay. Then, if I take the ratio of rotor gross rotor output to rotor input, gross rotor output, that is PM to rotor input, P2, then what I get? That is PM by P2 is equals to 1 minus S. And this equation is fairly considered as the rotor efficiency, not motor efficiency. Motor efficiency is grand output by grand input. This is rotor output, gross rotor output by gross rotor input. Okay, so therefore, rotor input. Therefore, it is rotor efficiency. Equation 10. Okay, so what is 1 minus S? Therefore, PM by P2, which is equals to 1 minus S, This I can write it as n minus ns, because n is equals to ns into 1 minus s from the equation of slip. Don't forget the equation of slip. Until and unless we breathe induction motor, we need slip equation. Okay. So therefore I can write gross rotor output to rotor input is equals to n minus ns. That is rotor efficiency. That is rotor efficiency is equals to n over ns. This is one of the important equations. And rotor copper loss to rotor gross output. Rotor copper loss to rotor gross output is equals to, I can write S divided by 1 minus S. Okay, S divided by n 1 minus S. Okay, so that is from this is from equation 7 and equation 10. From equation 7 and equation 10. So this is all about the power relations, torque relations, slip relations of an induction motor. Okay. So in the next class, we will start with the phasor diagram of induction motor. Okay. So there is a small assignment to you. Before coming to tomorrow's class, you please go through the phasor diagram of transformer on load condition. Okay, it is your duty. Tomorrow I will not explain the induction transformer phasor diagram. Okay, so tomorrow before coming to my class, tomorrow is second hour. Okay, so you have to go through the phasor diagram of transformer under load condition, and more importantly under inductive load condition, when the load is inductive in nature. Okay, it is your responsibility. Okay.